At this time, it is our pleasure to begin the webinar. Stay tuned after the presentation for the Q&A session. Please send your questions through the Ask Question box located on the bottom of your screen, and we'll get to as many of them as possible. Now I'll turn it over to Joshua to begin the presentation. Joshua?
Thank you so much for the introduction. In this webinar, I hope to use our time talking through a quick background of why the standard came about. What was the need for it? The history and overview of where the standard is today, some of the performance expectations, design, and key features that go into a B73.1 pump. We'll look at a range of available models, some key takeaways to summarize, and we'll look forward to fielding question and answers at the end of the webinar.
All right, great. So first we've got a poll. You should all be seeing it on your screen now. And it's asking, what is your role with centrifugal pumps? We'll give everybody about 30 seconds to answer, and then we'll keep moving. And we've got a couple more poll questions throughout, so we look forward to having you answer those. Okay, great. I'll give everybody just a couple more seconds. All right, so looks like we've got a little bit of a mix here, mostly engineers and folks in sales and distribution. Thanks everybody for answering that one. I'm going to turn it back over to Joshua.
Great. So starting this conversation of where the standard was or where the end users were prior to the standard. So we can imagine at this time, the history of using centrifugal pumps within the industry was quite large. So we measure right about 300 years prior to the standard. So this standard did not invent a centrifugal pump, but what we were looking to do with the standard is create dimensional criteria so that each installation would not require to be brand specific. So if you can imagine an end user at this time would need to be keeping to this brand while looking for services and spare parts, for example, whether they would experience a variety of reliability and performance would be between a potential gap between the manufacturers. So what the standard is looking to do is raise the bar for the experience of the end user to have consistency between these manufacturers. So the need, generally speaking, was equal amongst end users and manufacturers. And we'll go to highlight this relationship as we move forward in the webinar. So looking to the history of the standard, at publication, the B73.1 was published by ANSI in 1974. So you might in industry hear this term ANSI pumps or ASME pumps. It is quite interchangeable in conversation, but where it started was with simply 5 pump models and has grown to 27 pump models today. The primary goal of increasing the adoption rate and utility of the standard into the chemical and hydrocarbon process industry is first and foremost. I can note in historical updates listed here in the short-term summary is going to be quite impactful changes throughout the years. So it must be said every latest revision does have some level of anticipation before they get released. Where we are today is going to be at the current revision of 2020. So the namestate ASME B73.1 revision 2020 focuses on horizontal end suction single stage pumps, with the notable exception of solid polymer pumps have been adopted into B73.1, but for the conversation today, they will not be covered in the scope. Within the standard, you can expect to find dimensional interchangeability requirements, pump performance, and features to support maintenance, design requirements to also improve reliability. It does not include, for example, maintenance and operations requirements. Where this is included is in, for example, a maintenance manual that will be published by the manufacturers, and that will cover base plate leveling, grouting, etc. Final thoughts on where we are today. B73.1 simply covers overhung pumps, where 0.2 would cover vertical inline pumps, and B73.3 would cover sealless pumps, that being your mag drive pumps. The latest revision of the standard does broaden the scope to also include the following specialty designs, such as a self-primer, recessed impeller, low flow, and repeller pumps. Having shared common components across the B73.1 models, these bring the advantage of readily available parts. Although it must be said, these specialty designs do not require dimensional interchangeability and hydraulic coverages as outlined further in the standard. Looking into what goes for dimensional interchangeability, we can begin with some designations, systems, and sizes. So the designation systems, such as these letters AA, AB, and AC, are an easy way to identify which pumps are dimensionally interchangeable within the standard. For nomenclature, in the standard outlines suction, discharge, and nominal impeller to specify the pump sizes. And it can be said in conversation, sometimes this nomenclature is reversed to suction and discharge. But for this presentation, we'll be using these suction, discharge, and impellers to be pointing out pump sizes. So for example, a 313 will be your suction flange, discharge, and impeller diameter. So looking into a little bit more detail of what you get with dimensional interchangeability, it's the requirement for the manufacturer to provide mounting dimensions, the sizes of the flanges, locations of the nozzles to be interchangeable between manufacturers. Now, the distinction here is the standard does not require part-for-part interchangeability between manufacturers, and also does not require identical performance. And this is to be noted here, where typically the nozzle sizes will be the determining factor for flow rates, but in the standard there isn't this performance expectation between the manufacturers themselves. We'll go into a bit more performance in the following slides as well. So closing out this discussion on dimensional interchangeability ends with the base plate standardization, where the input shafts, base plates, and foundational bolt holes need to be interchangeable between manufacturers. And again, the same narrative where it does not require part-for-part interchangeability between manufacturers. So let's discuss now what you can expect to have capabilities with these B73.1 pumps. Head and flow is a typical requirement for end users when they're specifying a pump. Now, in the standard, there isn't specific flow and rate callouts. I will have to note in prior standards, there was a table that outlines flow as it relates to the pump size, but that has been removed. So in this language, we're going to say you can expect up to 7,000 GPM of flow and expect up to 900 feet of head. The standard outlines clearly the pressure, that should say the minimum pressure a manufacturer needs to meet is the class 150 flanges as outlined in ASME B16.5 or 1642 for the material used. So we like to say you can make the pump as beefy and robust as you would like. However, the failing point or the minimum pressure criteria needs to be outlined in the Class 150 flanges. The next clear criteria for capabilities of these pumps lies in the temperature. There's a line in the sand of 500 degrees Fahrenheit for your application. However, at 350 and above, it does specify oil cooling and jacketing to be made available for the application. Now, with this criteria listed here, we would suggest anything above and beyond these to likely be in the territory of an API 610 standard pump that would likely suit the application better.
Okay, great. We've got another poll here. So this one is, what is your preference to have a solid shaft or a sleeved shaft? Looks like we've got the wrong poll question here. If everybody will go ahead and answer, I'll get the other one set up. Okay, great. We'll come back to the answer here a little later in the presentation. For now, we have another poll question. So this is, what would be your expectation for the life of a B73.1 pump? So I'll give everybody about 30 seconds to answer. Looks like a good percentage of answers are already coming through. Just keep those coming. Okay, great. So it looks like that most people, about 45%, said 11 plus years, and close behind it with 6 to 10 years is about 37% of attendees. Joshua, do you have anything to add to that?
Yeah, I really appreciate the responses here. And it looks like, for the most part, the perception of these pumps is that these are reliable units that can last a significant amount of time, and just goes to show some of the credibility that has already been established within the industry. We like to note here the answer to this question isn't crystal clear in the standard. There is an outline for bearing life expectations. So clearly it states you need to have L10 requirement, which equals to 17,500 hours of life or 2 years of continuous runtime. And that standard is specifically talking to a worst case scenario of you run your pump at max RPM and, for example, at a shutoff valve, so deadheaded, and really creating, okay, what's the worst case scenario? And this is the bearing life suited to that. But as we can see, for the expectations and for the outline of the standard, we're looking to promote life well beyond that. So thank you.
Okay, great. Thank you.
All right, looking at a couple of design criteria. Now, this won't be an all-encompassing list, but just some outlines that I wanted to look over that speak to some of the requirements in B73.1 that promote pump performance and reliability. So first one is looking at the impeller types. You are able to choose 3 as the manufacturer for your design, either open, semi-open, or closed. And each of those has its pros and cons. I won't be getting into each of them, but just to let you know, that is within the standard for a manufacturer to specify. The external adjustment in a pump is also a requirement for the pump manufacturer to provide. That means we want to have the impeller clearance adjusted without disassembling the pump. Now, this will speak to a lot of the mechanics in the field where we can do this as a first pass if we're troubleshooting. For example, if the pump is not performing, rather than having to tear apart the pump, we can have this easy way to troubleshoot on the first pass. The impeller can be attached to the shaft via a keyed or threaded shaft. Again, these are options for the manufacturer to choose, but an end user can specify their preference as well upon purchase. And last note on design, it's a requirement for the manufacturer to have a back pullout assembly without unbolting the suction and discharge connections. Again, these features go a long way in promoting maintenance and upkeep for the pumps. Smaller mentions here for features are be example of tapped holes for jack screws and slots for wedges to be able to take apart the pump without damaging or causing any headaches there. So looking at this image here, we have a family curve of 1700 RPM with the range of small to extra large pumps. And what we wanted to note here is, it is a one shot, we can see exactly where the performance is going to be sitting for each pump model. On the far right side of flow, you can see 7,000 GPM for that pump there, the 10816. While at the highest end, one of the low flow pumps, the 3.513, is quite robust at that 900 feet for 3,600 RPM. So this chart, for example, the 1750, outlines what you can expect for the entire range of sizes for a B73 pump. Wanted to note here as well, there is a 4317 listed here. The standard hasn't actually adopted that size. This is, again, to that conversation of relationship between end user, manufacturer, and the standard, where the demand for that pump was driven by the end users, responded to by the manufacturers, and it is going to be just our guess or hunch that that pump will be adopted into the standard in the future. Now, going on further into specifically pump performance within the standard outlines the allowable operating region at a continuous state. So we like to say to the left of the curve is a minimum flow specified by the manufacturer, and the right of the curve is to be 120% of BEP. Now, this is what we call the AOR, the allowable operating range. It is quite broad, and the minimum flow is typically shown in the documentation for the pump performance curve, typically, for example, as a red line, to give you an idea of allowable operating range. That criteria is really determined by these three features: the shaft deflection, bearing life, and vibration. So the conversation is, what can your pump do, and then what should your pump do? Your pump should be in the preferred operating range. So the POR is also outlined. That's going to be a criteria of your critical speed. So between 70 and 120% of BEP as what you can expect to find outlined in the standard of the Hydraulic Institute 9.6.3. And the table outlines the critical speed as the manufacturer is free to design a shaft and impeller that is as robust or as thin as they find necessary. So again, the standard does have these outlines, but the part-for-part interchangeability and design features inside the spec does allow manufacturers to make these decisions here. So looking into the performance tests and inspections that are outlined in the standard are going to be optional, but when they are required, are to be compliant with B73.1 and within that Hydraulic Institute 14.6. The performance acceptance are held to the tightest tolerance band as outlined in that standard of grade 1B. These values are listed here in the table with mandatory requirements of plus or minus 5% for flow, mandatory requirement of plus or minus 3% for total head. Now, the standard also outlines either or requirements of power or efficiency, those values there. The standard will outline either of these can be a guaranteed optional requirement. So noting a bit more on the performance of the pump here, the standard outlines clearly the topic of critical speed. So for the first lateral, critical speed of the rotating assembly has to stay well above your max operating speed. And that is to say that if the pump is on VFD coming up to speed, its full speed, it should never pass through any resonance points. The standard calls for the vibration measurements to be taken at the factory facility under testing conditions with these criteria, the speed being plus or minus 5% and the flow being plus or minus 5%, and they're not to exceed vibration limits outlined in Hydraulic Institute 9.6.4. For example, for overhung pumps, that standard reads a maximum velocity of 0.15 inches per second for overall vibration velocity. So we like to think of our critical speed calculation as being things that we try and shoot for on pen and paper, while vibration requirements is putting the product line through its paces and making sure it meets that calculation. Now, within the standard, for us, it's very important to recognize where we see performance accountability for manufacturers. So as published, the performance curves are required by pump manufacturers to be within the stated tolerances for head and efficiency, plus or minus 5% for head and minus 5% for efficiency. Although B73 does not have a formal auditing process, the Hydraulic Institute does conduct periodic audit of test labs for participating manufacturers. In this note here that I've listed, the manufacturing conformity is confirmed statistically in a testing environment. There is a note saying 90% of pumps untested need to fall within these tolerances of head and efficiency. And so there is leeway for what we call quote unquote oddball pumps that fall out of the requirements. But again, as we've seen in the poll, the expectation for these pumps to last for many years is preceded with the reputation of this standard. And this performance accountability is a big part of making sure we see great reliability out of these pumps. Here, I'd like to take the time to give you a visual of a Hydraulic Institute approved test lab.
To further establish the quality and reliability of our pumps, our in-house testing facility performs rigorous testing of each pump design. Testing includes performance, NPSH, and vibration to ensure our pumps perform at the highest levels. Additionally, our engineering department is equipped with cutting-edge design technology, including 3D modeling, finite element analysis, and computational fluid dynamics, so that Griswold's design specifications are unmatched.
So continuing this conversation on accountability and compliance. So within the standard, the pump materials need to be within compliance of ASTM material specifications. So if I didn't state this before, the ASME B73 standard references quite a bit of partnering standards or partnering organizations within the industry to create this great accountability for these pumps. So the standard includes a broad selection of these materials from cast iron to titanium. Again, speaking to the standard wants to reach a great utility of hydrocarbon processing, general industry, and the sort. So within the ASTM specification does carry the requirement for chemical composition, mechanical property stipulations, and heat treatment. The typical common materials we do see in industry today as being readily available off the shelf, for example, will be your ductile iron, 316 stainless steel, carbon steels, and your CD4 duplexes. Examples for specialty materials that are listed within the standard, but typically are not readily available, will be your titaniums, your alloy 20s, and your Hastelloy C276. Closing out the standard for major requirements for a pump manufacturer will be the documents required upon pump purchase. So that would look like an outline drawing, a data sheet, a mechanical seal drawing, performance curves, and an IOM manual. For specialty requirements, we are going to be looking at, for example, a master document list, a parts list, allowable forces and moments on nozzles, certified mill test reports, and a statement of compliance. And here, this is where the communication between manufacturer and end user or the purchaser really comes into play. When you purchase a B73.1 pump, these are the requirements, but how the information is delivered, if it's clearly written, if it's delivered on time, really distinguishes that manufacturer within the industry here. It also creates the accountability, for example, a CMTR test report to have the heat numbers traced back to the pump to be able to identify exactly what's in that composition. So within the standard, there are a range of additional features for those that have preferences. I'll outline a couple of examples here. And the first one I wanted to take some time to look at is the solid shaft versus the sleeve shaft option. The portion that is going to be sleeved is right after the impeller, right where the mechanical seal or packing will be sitting. Now, these are going to be options that usually are typically preferred to by the site or by the specifier. I'd love to get your poll and understand just where we are with that split.
Okay, great. I'm going to move us back again. Sorry about that. If you didn't have a chance to answer before, the poll should be appearing on your screen now. It's what is your preference, to have a solid shaft or a sleeve shaft? And we'll give everybody a couple more seconds. I know a good bit of you have already answered this, but okay, great. Thank you, everybody, for answering that. So it looks like the most common answer here was solid with 41%, and then sleeved with 34%. Joshua, do you have anything to add?
Yeah, this is always a great perspective to see where the preferences lie. Within the standard, it's written as solid is going to be preferred for a mechanical seal installation, while the sleeved is going to be preferred for a packing installation. It has to be said that preference does lie quite split here, and it's a little bit funny for me to see what the preferences are, even no preference. But thank you for that.
Sounds good. Thank you.
Moving on for additional features. This C-face adapter, what it is, it's a rigid connection between a C-face motor and the bearing frame. Not very used in industry, in my experience, but it is one of those features that could be very well benefited for when you just require minimum or completely eliminate the need for alignment problems. This will promote extended coupling life, bearing life, and longer mechanical seal life. We'd like to say these installations will be great for maybe remote locations where aligning the pump or doing pump alignment work is not going to be possible. Another additional feature of this standard will be seal chambers. The three major categories, for example, would be a standard bore, large bore or large cylindrical bore, and a taper bore. The standard bore typically will be used for primarily packing and component seals, so it's a much smaller surface area for anything to fit there. The larger bore is when you start to see the installation of cartridge seals, as there's more room to fit. The taper bore is going to be typically the leading favorite in industry, as it prevents the accumulation of solids and has the promotion to be self-venting, and quite a bit of mechanical seals, single and dual cartridge seals would be able to fit in that envelope. Looking further into the mechanical seal within the standard does cover designations adopted by API 682, so commonly referred to as Plan 11s, Plan 23s, Plan 53As. This is a great example of the standard going as broad as it can to accommodate these flush plans. The Plan 11 will typically be your baseline, and the reason for going into anything else would be a process fluid that's either hazardous to your health or hazardous to the environment, and the sites will typically specify if it requires single or double mechanical seals. But for the support systems can still be fitted in the envelope of the base plate, for example. So some notable mentions within the standard that I would like to highlight here. Again, this is not the all-encompassing, but just notable mentions. The hydrostatic test of components does not allow visible leakage permitted, not necessarily hydrostatic test requirement for the pump, but at the component level. The casing and gland are to have 0.12 inches of corrosion allowance. We call this here the retirement thickness. So if a pump's in use and it has routine maintenance for the power frame, for example, or the mechanical seal, these three components, casing, cover, and gland, can be reviewed for these corrosion allowances and seeing if a pump needs to be retired or possibly repaired. The bearing lubrication system is most common with an oil bath. However, oil mist and greased bearings are also an option. Again, some things that are specified rarely, but are within clearly in the standard and can be used as an option. The impellers are to be balanced in accordance with ISO 21940 to meet grade 6.3 after final machining, and that really does guarantee the vibration levels are within check. The impeller is not allowed to just be casted and then installed in a pump. It has to go through this criteria here. So looking into some key takeaways here, want to close out this discussion when scoping a pump to fit your application needs to be fully compliant to B73.1 to provide the consistent performance and reliability of your horizontal and suction pump. Bringing that standard into your site will have a broad utility of use in chemical and hydrocarbon processing industries. Key features within the standard facilitate these ease of installations and maintenance for reliability. The dimensional interchangeability fosters a competitive market and guarantees end users with readily available product. And my final thought on pump performance accountability is select participating manufacturers have partnered with Hydraulic Institute to become certified 40.6 test labs. The market today has some great manufacturers that bring excellent products to the market. It would be our recommendation for the end users or purchasers to familiarize themselves with manufacturers that have taken the steps to become HI certified or Hydraulic Institute certified. Here at Griswold, we are proud to be fully compliant to ASME B73.1, as well as have a certified HI 40.6 test lab within our facility.